Also kann ich so eins und null wurde wirklich effizient die Logik das machen.
Is it good? Okay. So that's also working?
Yes, but
No.
oh.
No, you're not sharing it? Share it. You need to go back.
What?
Okay. Is it online?
It's frozen.
No, it's not frozen.
Okay. It's working.
Okay. It's all good? Okay.
Can you check the clicker as well?
Clicker. Looks like it's working. Usually it doesn't work. We still have 3 minutes, so I'm waiting. You guys can talk, don't worry. We're supposed to start at 14:15, right? Okay, good.
I wrote you already a mail about this. You didn't write back it. So how is this? Is this course like a requirement for the autumn course?
I'll discuss that.
Ah,
yeah, later. Yeah, sure. You can bump up the email if I don't discuss, or if you still have questions.
Because if the 3 people more come, no other student will be able to.
Hast du so vorgestellt? Ja. Ich habe es schon vom Ding her anders. Business administration. Business administration. Okay. Das heißt, Master Arbeit free. Ja, kann der Basic sein. Ja, aber Faktor. Was schon wieder Faktor und das Straf meint. Zusätzliche oder nochmal. Habe ich benutzt. Schon. Ah, schon. Wenn du einfach dort die.
Yeah, it's a bit tight here. Let's see.
Das ist ja schon Lisa macht es nochmal.
Nein.
Ah, das.
Das mit dem Wort mit der Queries.
Ah, aber die Dings. Was hast du das andere auch fest gesagt?
No. Okay, I think we can get started. Welcome to our cozy room on fundamentals of computer architecture. I hope you're here for this. There are more people registered, but maybe they're watching online, which is okay, actually, as we mentioned it over email. So today we have a lot of material to cover, but let's see how far we can go. This is a new course we're offering. I'm going to place it with perspective of other courses that we're offering and other courses at ETH soon. But before, I'd like to introduce myself and the teaching team, etc. Before I start, how many people here are EE students, ECE students? How are you? Okay. How many people are CS? How many people don't belong to any of those categories? You're in different departments, which is perfectly fine, as long as you've taken the computer engineering course. Okay, so let me start. So I'm a professor at ETH Zurich in the EE department. I'm also affiliated with CS. I've been here for about 9 years. Before that, I was at Carnegie Mellon at both EC and CS. Before that, I started the computer architecture research group at Microsoft Research, which is quite interesting. And some of that experience influenced how we actually cover this course, of course, and other courses too. I do research in computer architecture, as you see down here. And I worked at Google, VMware, Microsoft, as I said, Intel, AMD, and I spent a sabbatical at Stanford recently. And before all of that, well, during all of that also sometimes, I got my PhD in computer engineering from UT Austin a while back. And I think before that, I was kind of in your shoes, a bachelor student in computer engineering and psychology at University of Michigan. So that's kind of a summary of my academic career, let's say. You can find more information about me online, and you can email me anytime. My email tends to be very, very crowded. So if you don't get a response, which some of you have experienced, don't despair. Feel free to send it again or talk to me during course. I do research and teaching in computer architecture, which is the focus of this course: computing systems, hardware security, bioinformatics, genome analysis. And these are some research areas, some of which we will cover in this course, but we will not go into everything clearly because it's a limited time frame. My co-instructor is sitting in the back over here, Mohammed Sadr Sadati. He's a senior researcher and lecturer in my group. He is leading this course also. And he got his degrees at Sharif University of Technology, which is one of the top institutions in Iran. And you can talk to him and email him at any time. He has research and teaching interests that are quite varied. And do you want to add anything, Mohammed? Okay. He'll be giving some of the lectures, and there will be some other lectures also that might be happening depending on the material and travel schedules, etc., from some of Sapari students, etc. We might have some actually guest lectures too. Let's see. Any questions? Does that all sound good so far? Okay. This is the research group that organizes this course. You may see some of them here, but not today because we wanted to keep the seats available for people. Yeah, it's a cozy room. I'm not sweating yet. Let's see. Once I start sweating, it's going to be time to change the room, maybe. You can learn more about our research online. I'm going to go through these relatively quickly. As I said, we do research in the areas that I mentioned, and we have a lot of material online talking about our research, and I'm proud of the students that we have in the group and also that have graduated. You can find more about them if you're interested. There are a bunch of interviews if you want to learn more about future of computing from my perspective. You'll see some of it today and later, but there's more. Okay, there's a lot of material we put out that I'm not going to talk about right now. As I said, we do research in enabling fundamentally better computers. And today, computing is very interesting because we have a lot of heterogeneity, a lot of different types of devices that can process data, right? There used to be a time when I was doing my bachelor's, for example, or even PhD, CPUs were the dominant type of compute engines. Today, that's no longer the case. In fact, one could argue that CPUs are not as important, although I would challenge that, as we will see. There are clearly GPUs. GPUs were just starting while I was a bachelor student, and while I was doing my PhD, they weren't popular yet. Today, GPUs are a fundamental part of the computing landscape because of machine learning and other workloads that actually are happy with GPUs, let's say. So we're going to cover both CPUs and GPUs. Today, we're going to start with some basics that you hopefully have. I'm going to ask you questions related to that also. But also there are other accelerators. People are actually developing accelerators that are quite interesting, which we will cover some of them, some of the principles of there. Some of them are single instruction, multiple data accelerators. Some of them are systolic array-based accelerators. So there's a lot of heterogeneity. And there's also very specialized processing that's happening for machine learning, vision, media processing, compression, decompression, etc. So it's a quite exciting time to study computer architecture, I think, because there's this proliferation of types of computation, types of computing that are happening. And there's also a lot of innovation on the memory side as well. Traditionally, processing and memory have been kind of decoupled from each other, and there's a dichotomy between processing and memory. But people are trying to push more processing to the memory side, to the storage side, so that we can reduce the impact of data movement on performance and energy. And this is already happening in industry. We'll actually have some lectures related to that in the later part of the course. Okay, we do research in these areas, so I'm quite excited about it. As you can see, I kind of went longer than expected, but you're going to see this kind of slide later on. Okay, so these are some of the research topics that we look at, some of which you will see in this course, but this is not a, we'll see a lot of basics in this course, as you will see. We look a lot into robust, safe, reliable, and secure architectures. Energy efficiency is very important, because energy efficiency in today's world is really performance. If you make a computer more efficient, consume less energy, you can use more computers. That's one example, right? Or you can parallelize the program better across more computers. And we're looking a lot at the memory-centric architectures. Low latency architectures, predictable architectures are important. I'm giving you a lot of keywords, but a lot of these have a lot of depth in it, clearly. And clearly, I cannot cover everything in one slide. But think of this as the breadth of research that's going on in computer architecture. Also, there's a very interesting direction that's happening today, which is using machine learning techniques or AI techniques to design better architectures, either to ease the design of the architectures or to make the architectures much more capable than what a human can do. And we're going to maybe see some of these later on. And of course, there's the flip side of it, which is really designing architectures for better machine learning, better AI, better genomics, medicine, and health. Okay. So this is the transformation hierarchy. We're going to talk a little bit more about that. This course is kind of situated here, which is the hardware-software interface, ISA, instruction set architecture. People are hopefully familiar with ISA, right? That word. Okay, that's great. Computer engineering covers that. Today, we're going to cover mostly what computer engineering covered, maybe in a different way. But today was going to be kind of basics, hopefully review for you. But feel free to ask questions, because I will probably cover it in a different way. And microarchitecture. In this course, we're going to cover a lot of microarchitecture, but we're going to talk a lot about software-hardware interface also. But we're also going to take at some points a much larger view, which is, in my opinion, where things are going, both in research and industry, which is really co-designing across the stack. So if you want to really achieve the highest efficiency and performance and robustness and security, you really want to co-optimize across the stack as opposed to optimizing individual pieces. And this is already happening. For example, people are designing machine learning systems, right? They're really optimizing the algorithm and hardware together. We'll talk about that in systolic arrays, for example, when we go to that. And also the larger scale systems are like that. People are also thinking about devices, designing devices that can do better machine learning. These could be, for example, devices that can do analog computation or matrix vector multiplication in the analog domain. When we talk about processing in memory, we'll also talk about that. So that's very interesting, I think, today. Okay, so I already said a lot of this, I think. I think if you want to achieve the highest efficiency, performance, and robustness, we probably need to take the expanded view of computer architecture and co-design across the hierarchy and specialize as much as possible within the design goals that you have. Is this interesting? Okay, great. Yeah, I mean, we're going to see some examples of this, but we will, as I said, there are a lot of basics that we will cover in this course. That's why it's called Fundamentals of Computer Architecture. But I'm going to inject some of the examples of this later on. Today, for example, if hopefully we'll get to it, we'll talk about data dependence handling in processors. And when you do data dependence handling, you can do the data dependence handling in software or hardware. If the compiler does the data dependence handling, it has to know the underlying microarchitecture of the processor so that it can decide which instruction comes after which instruction, right? So that's an example of cross-layer design at a limited perspective, which is compiler microarchitecture co-design, right? You can also do it purely in hardware. which we will see in later lectures, out-of-order execution, for example. It does data dependence handling, detection, etc., purely in hardware. And that's another approach. That's a more microarchitectural approach. But people have proposed many different ways of doing this across the stack, and which is quite exciting also. But we may not be able to cover all of the ways. Just to keep that, you keep that in mind. Okay, so I'm quite a believer in teaching and research being two sides of the same coin. So I actually inject a lot of research topics and ideas into even the most fundamental courses. So don't be surprised by that, because in the end, I think these two things drive each other. If you do research, you discover something and you educate the community, and at some point it becomes teaching, meaning everybody knows about it. Then essentially, if you teach all of these concepts, research becomes much better also. So, okay. So our courses, I'm going to get to, you can access this course as well as other courses online. I think there are links in all of these slides. Let's talk about some logistics. Any questions so far? Okay, great. So basically, we will try to study how something like this works as much as we can, building upon your previous knowledge on computer engineering. Hopefully, we'll cover essentially compute parts, memory parts, as well as storage parts. So I'd like to take a broad view of this lecture, but this does also mean that we cannot go into a whole lot of depth in everything. And if you want to go to depth, you should probably take the next course, which is the advanced, well, it's called computer architecture, but it's a more advanced master's level computer architecture course, or do research in the area. Let me put this course in perspective. So why are we offering a new course? It's actually a lot of work on us to do more teaching. But I think this is kind of filling a gap. So we have this digital design and computer architecture course, which is offered every spring. It's a bachelor's first year course, but it's mostly for computer science students. It's required. It's a required course for computer science students. It's a course that's broader than FOCA, which is this course, I would say. It's more credits also. But there will be some overlap in topics. In fact, there will be quite substantial overlap, but FOCA will also go into a little bit more researchy topics than DDCA does. We offer computer architecture every fall. This is master's level, as I said. Usually a mix of CS and EC students take it. This is more advanced topics than FOCA. So if you take FOCA and if you take computer architecture, that's okay, I think. Or if you take DDCA, if you've taken DDCA, probably none of you have taken DDCA here, right? Yeah. If you've taken DDCA, I wouldn't recommend taking FOCA, this course. I would recommend taking computer architecture after that. We also offer an orthogonal course, which is a seminar course in computer architecture. It's offered every fall and spring currently. This is mostly bachelor students, but sometimes masters and even PhD students take it. Again, it's a mix of CS and EC. And this is also good to take after DDCA or FOCA or even computer engineering, actually. Okay, so what's missing here, I guess? Well, there's also computer engineering, which is offered by Kaveh Razavi every spring. This is a bachelor's second year course, EC students, and it's a prerequisite. I hope everyone has taken it. Okay, that's good. You enjoyed it, I hope. Otherwise, you probably wouldn't be here. That's my guess. But this covers some OS and basic computer architecture concepts. So basically, what was missing is a course for, I call it ECE, but it's really EE, I guess. I'm used to the CMU terminology, electrical and computer engineering, but electrical engineering is also fine. Essentially, what was missing was some course that kind of bridges the gap between computer engineering and computer architecture, a master's level course. And this FOCA is really bridging that gap from my perspective. Basically, we will cover computer architecture concepts. If people have taken DDCA, I don't think there's any need to take FOCA. There with substantial overlap. So we'll have a subset of DDCA plus some advanced topics, as I said, and we'll have hands-on labs. Does that sound good? Does it answer all the questions related to this topic? Yes, please.
I can ask in the break actually, but
yeah.
If I'm in the masters and I don't have FOCA or anything else, and I can't actually use FOCA for my masters.
Okay, maybe this is a special case we can discuss over the break. Yes, as a master's student, I think you should be able to have some flexibility. But again, this is every individual case is different. Okay. Any other questions? Okay, good. So what is our goal? Essentially, it's similar to a lot of our courses. We'll cover a lot of basics. We'll cover a lot of principles. I actually think about principle design a lot. And we'll cover some precedents, like what people have done in the past. Again, there's a lot of words over here. You can listen to me instead of reading the slides, etc. You can always read the slides later. Basically, my goal is to build an understanding of how a modern computer system works underneath. Again, building on computer engineering. look at hardware-software interface of modern computing platforms like GPUs, CPUs, systolic arrays, processing in memory, etc. And give you the ability or the tools to evaluate trade-offs and different designs and ideas. And we're going to have labs to implement and simulate various components. They're going to be simulation-based labs, mostly. We'll try to have some hands-on FPGAs, but let's see if we can scale up the infrastructure to that level. And hopefully, through that, you'll learn to systematically debug increasingly complex systems. And people do simulation before they design things, actually, in industry. If you go and design every idea that you have, then you'll be in trouble because you'll never be able to explore. Right? Okay, and hopefully all of this will enable you to design things better, evaluate trade-offs better, but also develop novel and out-of-the-box designs. Because in the end, those are the things that advance the state of the art. And that's what people are trying to do. I think my DeepSeek example is one example that I like because those guys went and really understood how to optimize things in hardware. Even though a lot of the concepts they used were known concepts, let's say. Okay. So hopefully by the end of taking this course, you'll be able to do better than DeepSeek. Okay, so these are the course components. Lectures, you're here. Readings, we're going to assign readings. We'll have optional homeworks. I'll talk a little bit about labs and exam because labs is important, I think. Exam is test of understanding or one sort of test of understanding. I'm not a huge fan of exams in the end, but the bachelor's level will have to have it. And there are some extra credit assignments also. My advice is don't focus too much on the exam. Since it's an optional course, hopefully you're not focusing too much on the exam, but I understand the focus also. Just focus on learning and scholarship and understanding. Basically, yeah, I already said this. I would suggest reinforcing problem-solving skills with homeworks. Do not worry about the exam while listening to the lectures. I think it's good to understand things here, and to study for the exam, you can actually do the homeworks, maybe go over the concepts in the lectures, etc. Does that make sense? Yeah. Okay. And we will release a lot of material to help you with the exam at some point. It's not going to happen right now. I think the exam is in August or so, right? Sometime, yes. That's also another unfortunate thing. You'll have the classes will end and you'll have 2 months of break. Anyway, okay, that we cannot change. So I think my summary, this is the way I view things in general also. Focusing on learning and scholarship is good. Well, learning is for life, exam is only once. Right? You'll forget about the exam 20 years down the road. But maybe you will not forget about how a systolic array works, and it may inspire you to do something completely different, right? Okay. So that's what I mean by over here. I think most importantly, perhaps, trade-off analysis and critical thinking and decision-making is very important for me. If you can get those, that's great. Because the concepts may also disappear from your memory, but the ability to do trade-off analysis, upsides, downsides, critical thinking about concepts, hopefully those are things that will not disappear that easily. Okay, and also we have a lot of flexibility, I think, that we provide to students. Like you don't have to attend the classes here, you can be online. So choose what works for you. You don't have to be here, but if you're here, maybe you get a different kind of discussion. It's harder to, which is harder to get on Zoom, I believe. Any questions? Yes.
You mentioned that there's like a bonus grade, I believe, for extra credit assignments. Is that the oral exam that we saw on the My Studies page? There's like I mentioned like 30 or 50% oral exam or something.
No, okay. Is it oral? No. I don't remember oral, but we should check if it's there. But the exam is going to be written, but then extra credits is going to be totally different. So maybe, for example, we'll assign a paper to review, and we'd like to get your critical analysis of it. Right? And you may get 1 point, let's say, for the entire course. I'd like to make this course a learning experience for you as opposed to an experience where you focus on the exam. Okay. Okay, why study computer architecture? So what is computer architecture? Probably you've seen this before in computer engineering. Is it correct? Or something like this. At least this is my way of seeing computer architecture. It's really the science and art of designing, selecting, and interconnecting hardware components and designing the hardware-software interface to create a computing system that meets functional, performance, energy consumption, cost, and other specific goals. This is the limited definition, and I'll keep it at this. But if you broaden it, you can actually add the software stack and programming language, etc. But that's quite broad. Have you seen this before? Okay, that's good. Yeah. And I call it both science and art, as you can see. Well, you can add engineering also, of course. These are engineering and science are debatable in some cases. But art is also here because you really need to make some design decisions without knowing a lot of things. You cannot model everything in the world, right? For example, this thing is quite successful, not necessarily because they predicted what kind of workloads were there. They had their judgment call also. Okay, so wide-study computer architecture. We'd like to enable better systems. Our systems are unfortunately still not good, as we will take a critical analysis of it. We want to make them faster, cheaper, smaller, more reliable by exploiting advanced and changes in underlying circuits, as well as looking at workloads. We'd like to enable new applications in a much better way. And clearly, we're seeing that a lot these days, right? Self-driving cars, personalized genomics is an area that I'm quite interested in. Like lifelike 3D visualization, it's becoming much better right now, but 20 years ago, it was very different. Machine learning, large language models, etc. Enabling better solutions to problems is also important. Again, I will not read or discuss everything in the slide, but you can go over these slides. This is an overview. And I think understanding why computers work the way they do is really also important, because all of these are interesting for sure, and they advance. But sometimes if you don't understand how computers work, you may not be able to optimize even existing systems. Right? And that's why I'll bring back the DeepSeek example. These guys actually really figured out how to, they really understood why computers work the way they do, and they really optimize things better. Okay, so today is a very exciting time. I already talked about this, so I'll go through this relatively quickly. But basically, there are many different potential systems possible, and there are many different types of computing and memory and storage units that are out there. Today, the domain of computing is very heterogeneous, which was not the case, again, 25 years ago, 20 years ago, etc. And there are many difficult problems that happen because of this, as well as that lead to this. Clearly, data-intensive applications, power constraints. The reason we have accelerators that are very specialized is power constraints mainly. Complexity of design. That's why we have heterogeneity as opposed to having a single processor that's extremely complex, right? Difficulties in technology scaling. We will see some of these. Memory bottleneck. That's going to be important to look at. Reliability problems, programmability, security, and privacy issues. These are all different aspects also of computer architecture, as you can see. Probably I've forgotten some too. Okay, and there's no clear definitive answers to these problems, which enables innovation, essentially. If you actually have a good idea, good solution that solves a problem in the space, you can actually have your potential niche market, right? And maybe that market will grow. That's kind of what happened with GPUs, right? There was a very niche market for graphics, but over time, its parallel processing power was useful for different applications that could actually take advantage of it. Okay, as I said, computing landscape is very different from 10 to 20 years ago. Both applications and technology demand new architectures, and every component and its interface, as well as entire system designs, are being re-examined today. I've shown you this picture before. This is an example system in your pocket, for example. This looks very different from a system 20 years ago. Inside this, there are a lot of accelerators, and this is actually not a single chip. This is a chiplet, right? There is a high bandwidth interconnect between these two chips, let's say. Okay, I think that is an example of system that takes advantage of that expanded view, actually. There's a lot of across the stack optimization that happens over here, which we may get into sometime. Before I get into it, I think there are a lot of opportunities. We saw this picture of problems and electrons at the bottom, right? You can think of it at the top and the bottom. I think there is a lot of opportunity at the bottom today, meaning we need to examine new technologies, new materials to make computing much more efficient. Quantum computing is one example, but it's not the only example, I think. I think we really want to look at new materials that are much more efficient going into the future. And this is actually called, there's this famous saying, there's plenty of room at the bottom, which is from Richard Feynman, who was a famous American physicist. And he basically imagined that you could directly manipulate individual atoms to do things for you. And this, again, I will not go into a lot of detail over here. You can read more about it. But one of the things that you could do this way is much denser computer circuitry. And he actually imagined swallowing the doctor, which is actually designing robots, nanoscale robots that can actually do things in your body. So I think this is actually good to think. The reason I'm talking about this is a lot of things that we take granted today are actually enabled by these very, very low level, what is called the bottom, right? Advances in electronics and devices, essentially. So it's good to think about that. And of course, all of those are enabled by exploiting them in a microarchitecture or architecture that can be programmable at the top. So the top is also important. Bottom is not the only thing. If you just come up with some fancy device at the bottom, and if you don't connect it to the top, your device is useless, essentially, right? And this is, I think, a challenge, a huge challenge that people are having with quantum today. There are a lot of challenges in quantum. A lot of them are technology challenges, like how do you make it cost efficient, etc. But one of the huge challenges is how do you really exploit it at the algorithms? And is the exploitation that you do at a very general purpose level with a lot of algorithms going to be successful? Meaning, is it going to be better than existing systems? Right? So top is extremely important also. And there's another paper that talks about top, especially with the lower level not scaling very well. Innovations in algorithms, architectures, and software are going to be more important. So as I said, I think these folks actually argue what I just said. I think in the end, we should really consider both. There's plenty of room both at the top and the bottom, but much more so when you communicate well between and optimize across the top and the bottom in the end. And you'll see some examples of this today and later. So that's why we take this expanded view that I mentioned multiple times now. Any questions? Okay, so let me talk about course info a little bit more, but we're not going to spend a lot of time over here. I already introduced instructors. I should introduce the head assistant over here, Konstantina. She's also a senior lecturer in our group, and she's going to be coordinating the course as well. Do you want to add anything, Konstantina? Konstantina received her PhD from NTUA, I guess the top school in Greece. And then we have a bunch of assistants and guest lecturers who are actually part of our group research, both researchers as well as PhD students. I don't know who's here. Let me see. Konstantinos escaped. He was the person who set up all of this, but he escaped. I see Susanna and Jikun in the back. And that's all, because we told people not to come so that you can have seats over here. They might be online. Okay. So if you need help, there's Moodle. You can always email us, but Moodle is preferred for especially technical questions. But if you have some individual question related to your course attendance, etc., or how you're doing in the course, you should email us. We'll have office hours, so please come to them. You probably have seen the website. We have a website. There's a lot of information that we will add over here, and we will send email as well. I don't want to go over this, I think, but maybe what I will say over here is definitely attend the lab sessions, because info about each lab and its evaluation will be provided in the lab sessions. We intend to have 4 labs. Let's see. And labs will start on March 6th, tentatively. Anything else you want to add over here? Okay, good. Final exam. So it's a written exam. We will talk more about that later on. But as I said, optional homeworks could be useful to study for this. I think this is a simple way of the grade evaluation. But again, as I said, don't focus on the grades. Focus on learning. Okay. Okay, now I'm done with the introductory material. Any questions? Otherwise, I'm going to jump into some things that you probably have seen, and I'll ask you questions of it also. So I like this quote from Hamming. I don't know why this. Yeah, the purpose of computing is to gain insight. This is Hamming and his cat. Do people know about Hamming? Hamming codes? Yeah, some people know, some people don't know. Hamming distance. Okay, maybe I'll talk about that later. I want to cover the basics right now, but remind me to talk about Hamming distance later. But Hamming actually came up with coding theory, at least a lot of it. And the codes that he developed are used in error correcting codes in modern machines. We'll talk about Hamming distance later, I think. But basically, his view was really, computers were viewed as computational devices, but he really viewed the computers as doing computation to solve problems. And that's actually a good view of computing. And in the end, you have a problem and you want to solve it by orchestrating electrons, right? At least in today's technologies. So how do you do that? If I had a way of talking to electrons and told electrons, solve my problem, that would be nice, right? Maybe that'll happen at some point if machine learning actually advances to that stage I have my doubts. But the reason we have this levels of transformations, we cannot bridge this gap. And to bridge this gap, we express our problem with an algorithm. Again, I will not go through the details of what an algorithm is. Hopefully you've studied that at some point. Have you? Okay, good. But I provided for your benefit over here, at least our definition. And then you implement the algorithm in a programming language, write it in a program, and then that gets executed partly using system software mechanisms, virtual machine, operating system, memory management. And then both the program as well as operating system execute using on top of the hardware-software interface. They basically have instructions that are specified using an instruction set architecture, which is really the contract between software and hardware. It's really what the programmer assumes hardware will satisfy. So that's the definition of instruction set architecture. You've probably seen that before. That's good. And then that instruction set architecture gets implemented using some microarchitecture, as we will see soon. And microarchitecture gets implemented using logic gates, digital logic circuits. These are building blocks of microarchitecture, for example, gates. And then those logic gates get implemented using devices like transistors, etc. And transistors operate based on principles of physics, which is what moves electrons. So that completes the picture over here. So in this course, we're going to talk a lot about over here. We may go into logic a little bit today. Probably you've seen the difference between ISA and microarchitecture. I think of ISA, well, ISA is really the interface, right? Interface between what the programmer assumes, what the hardware will provide. And I think there's a nice analogy over here with cars. Cars have very similar interfaces, right? The gas pedal, for example. Well, self-driving cars are a little bit different. Maybe in the future, you will not have this interface either. A different interface will change. So the ISA is changing, as you can see, but it changes very slowly. You still have these cars. And the gas pedal is really the interface for acceleration. But internally, at the microarchitecture level, there may be many ways of implementing that acceleration, right? You could implement it using mechanical parts completely. You could implement it using an electronic, completely electronics part potentially. I don't know how to do that yet, but you could implement it using different ways essentially. And that's really the internals of the engine and what happens after you press the accelerating button. And that's very different in many different cars. So that's the difference between ISA and microarchitecture from my perspective. And the user, the driver of this car, doesn't need to know anything about the underneath. Do you agree? When you drive? But sometimes it could be helpful, right? You may decide to press the button like 50% if you knew actually how efficient your engine would be if you press the button at different levels, let's say. So actually knowing the underneath could potentially enable you to optimize the system better. This is my poor man's explanation of how you can optimize across the stack, right? By knowing what's going on underneath. Okay. So implementation, microarchitecture can be different, various, as long as it's satisfied the specification. For example, you can have an add instruction. It's the same in the ISA, but then adder implementation can be different across different microarchitectures. It could be ripple carry, carry look ahead, bit serial, etc. So I'm going to refer a lot to Harris and Harris book, which we will recommend. You can find it on our website. Have you studied adders? No, not in, somewhat in computer engineering or something else. Oh, Digitech. Okay. 2 years ago. Okay. So you remember any of these? Ripple carry, carry look ahead? A little bit. Okay. Yeah, that's okay. I mean, you don't need to really know this for this course. I'm not going to ask you carry look editors, etc. Clearly, there's actually a computer arithmetic field that is actually quite exciting. And it's actually really important today, especially because of efficiency of machine learning, because a lot of machine learning is really about computer arithmetic in the end. How do you implement matrix vector multiplication? But these are there are many different ways of implementing adders where the trade-off is latency, cost, area, overhead, bandwidth, etc. We're not going to go into that. If you're interested, you can look more in this Harris and Harris. So similarly, x86 ISA has many implementations, right? For x86 is the ISA that's kind of dominant today, although it's changing, I think, over time, at least in general purpose computers. There are many, many implementations by especially Intel and AMD. And microarchitecture usually changes faster than ISA. There are few ISAs, like x86, ARM, SPARC, MIPS, Alpha, RISC-V, etc. And there are GPU ISAs also. It changes, but many microarchitectures, because microarchitecture is easier to change, right? It doesn't, when you make a change in the microarchitecture, the program doesn't need to change. So there's a huge software stack gets built on the ISA, but you can change the microarchitecture to speed up programs without changing any of that software stack. Makes sense. That's the reason. And we see a similar example over here, right? This gas pedal has not changed for many decades, but underneath there has been a lot of innovation in engines. Okay. So microarchitecture is the implementation of the ISA under specific design constraints and goals. You can also think of it as anything done in hardware without exposure to software. This is a kind of way of thinking about it. So pipelining. You've covered pipelining? You know about pipelining? Okay. So today we're going to go up to pipelining, hopefully. In order versus out of order instruction execution. Have you covered out of order in detail? So that's what we're going to start with, especially next week in the second course, hopefully, if we cover the basic materials. But if you tell me that you know everything about pipelining, maybe we'll start with out of order without covering the basics. So that's going to be important because all modern microprocessors are out of order execution processors. Pipelining provides throughput. Out of order instruction execution makes it much better. Memory access scheduling policy, speculative execution. Probably you've seen speculative execution. Yes? No? Okay. Branch prediction, for example. Have you seen different techniques for branch prediction? Touchdown. Okay. So we're going to go into more. Okay, that's great. Okay, in 30 minutes. We're going to go longer in that. So you don't know about perceptron-based branch prediction, for example. Okay, good. That's a good test. Superscalar execution. Basically fetching multiple instructions per cycle is a simple concept. Clock gating. These are actually all examples of microarchitecture. Normally, these are not exposed to software. That's why I'm calling them microarchitecture. But you could expose pipelining to software also. You could imagine an ISA that says, oh, these are my pipeline stages. And the software can schedule things on the pipeline stages. It'll be an ISA that doesn't give a lot of freedom to implementation to the lower level hardware designer. So placing the ISA is important, but we're not going to cover a lot of that in this course. If you're interested in that, DDCA is the place. Caching, prefetching, voltage and frequency scaling, error correction. I put question marks over here because that really depends on whether the cache, prefetcher, etc., are exposed to the ISA, exposed to the programmer. So the key test is really, is something exposed to the programmer? Does the programmer need to know about it when they're writing programs? And this could be any programmer. Okay, let's play a fun game. Property of ISA or microarchitecture. Opcode of an add instruction. What do you guys say? ISA? Okay, ISA people are correct. I'll go through this relatively quickly because this is very basic, I think. Type of adder used in the ALU. ISA? No, microarchitecture. Okay, I kind of fooled you there. Yes. Number of general purpose registers. Yes, go ahead. You can blurt it out, no problem. ISA, yes. Number of cycles to execute the multiply instruction. Blurt it out. Micro, yes, I'll go with micro. Although that depends on the execution model, as we will see. We'll cover, for example, VLIW, very long instruction word architectures. Have you heard about those? No? Okay, good. Now we'll see that in later execution. This is a paradigm of designing computers where people said, okay, we're going to expose the latencies of each instruction to the compiler so that the compiler can actually extract parallelism and schedule everything statically. This way, hardware is simpler and much more efficient. Compiler is complex, but hopefully it does a good job. Okay, number of ports to the register file. How many things can you read from the register file concurrently? Micro, good. Whether or not the machine employs pipeline instruction execution. Pipelining, basically.
Oh, usually micro?
Usually micro, yes, exactly, except for maybe VLIW. Yes, that's good. Program counter. Yes, okay, good. Okay, good. I think we're at a good place here. All right. So now that we know what an ISA is, how do we implement it? And you've seen some of the implementations, but there are many, many opportunities for implementation here. In other words, how do we design hardware that obeys the hardware-software interface? In other words, how does a machine process instructions? What does processing an instruction mean? And for now, I will assume the von Neumann model, but we will break that later. You heard about the von Neumann model? Okay, good. So it's going to be a little bit of review. But basically, von Neumann model has two properties. Okay, maybe you can tell me what those two properties are. Two major properties, yes.
Yeah, memory and you have like processing
Okay, that's good. I mean, that's part of the, I wouldn't call them as major, but yes.
I would say only have like one pipeline between the processing unit and the memory.
Yeah.
So we store both code and memory.
Okay, yeah, stored program execution. Yes, I think maybe you guys are getting to the same thing. There's stored program computer. There's one more thing that's actually going to cause a lot of trouble to us. That's why we're going to do out of order execution. Hint, hint.
The self-modifiable code.
No, not necessarily. But that causes problems also. That could be, in a one Neumann model, you could actually say self-modifying code is not allowed. Sequential execution. Basically, maybe you mentioned that, I don't know. Maybe you were going to, sorry. But basically, every instruction is executed sequentially in the one Neumann model. No instruction can be started before the previous one can be completed. That's the strict definition. But in the microarchitecture, you can violate that as long as you report to the software that everything's in order. Okay, so we're going to see that basically. That's what out of order execution is all about. Okay, so basically, we have architectural or programmable visible state before an instruction is processed. And then we process the instruction. And then we get architectural state prime, which is what happens after the instruction process. And ISA specifies how to transform AS to AS prime. You can think of an ISA as a finite state machine, actually, if you think about it, where the inputs are instructions. Okay, processing an instruction means, as I said, I think, transforming AS to AS prime according to the ISA specification of the instruction. Okay, these are the two major things in a one Neumann model, although there are other things that you mentioned also. Basically, stored program, sequential instruction processing. And yes, the one Neumann model is usually associated with this picture, which is decoupling the processing unit and memory. So that's true. But then there's other parts also, actually, output, input control unit, etc. And again, in DDCA, we cover this in a lot more detail, but I'm not going to do that right now. You've probably seen some version of it in computer engineering. So what is programmer visible state? This is architectural state that's visible to software, essentially. Programmer sees all of these and can modify it. Memory is an example. It's an array of storage locations indexed by an address. Registers, which could be general purpose versus special purpose. And there's the program counter that you guys all got correct. And instructions and programs specify how to transform the values in this architectural state to the next values, essentially. Make sense? So architectural state is programmer visible. But then there's also microarchitectural state that's not programmer visible. Okay, so we're going to add more and more of that as we go along. Okay, process instruction step. I said this already. ISA specifies what AS prime should be given an instruction and AS, architectural state. Microarchitecture implements how AS is transformed to AS prime. So as I already said, ISA can be viewed as an abstract finite state machine, where state is programmer visible state, next state logic is instruction execution specification. Hopefully these are things that you're kind of familiar with, at least. If you have a finite state machine, you have states, and you have a way of going from one state to another state. And next state logic determines how you transform from one state to another state, essentially. And that next state logic is combinational. And the fact that you're moving between different states is sequential, essentially. Okay, from an ISA point of view, basically, there are no intermediate states between AS and AS prime. That's what the programmer assumes, essentially, right, during instruction execution. One state transition per instruction. Where microarchitecture is a different mindset, essentially. There are many choices in implementation over here. We can have programmer invisible state to optimize the speed of instruction execution. We can have multiple state transitions per instruction. For example, one choice is actually implement things exactly as ISA specifies them. Bad idea, as we will see. This is single cycle machines. You may have heard of that. Have you covered that in computer engineering? Okay, maybe you called it something else. I don't know. Yes.
We first designed it, and we first designed like a CPU architecture, and then we split it up into like 5 parts to like look at how going with like small clock cycles, doing each one stage is like faster than just doing one clock cycle.
Okay.
Which was all.
Okay, exactly. Yes. So it's essentially the same thing. Doing one clock cycle in one at one go. I'm going to cover it in a different way. So maybe you wouldn't call it exactly single cycle machines, but this is choice one, which is a bad idea, as we will see. Using a principled framework, we're going to evaluate it. The other choice is what's called multi-cycle architectures, which may be one of those dividing it. But there are different ways of dividing it. Pipelining is also dividing it. You basically go through multiple cycles take multiple clock cycles to transform AS architectural state to architectural state prime. And for this, you need microarchitectural state transitions. And while you're doing that, you should not change the architectural state so that the programmer doesn't get confused, right? Because these are things that you're doing to execute the instruction, and the granularity of visibility for the programmer should be the instruction, right? Not microarchitecture. Okay, so let's go through this relatively quickly. I'll give you, sorry, I'll eat into the break a little bit, but then hopefully we'll start again. Essentially, I don't want to break it in a not so, let's say, nice place. A very basic instruction processing engine takes essentially is designed to such that each instruction takes a single clock cycle to execute. Meaning there's only combinational logic used to implement instruction execution. There are no intermediate programmer invisible state updates. And then you update the architectural state, which is essentially registers and memory. Okay, so this is basically what we're going to do. Process instruction in one clock cycle so that you transform AS to AS prime. And single cycle machine looks like this actually. You have sequential logic, which is the architectural state, which stores your architectural state. And that architectural state is fed into some combinational logic that implements your ISA, essentially, every instruction specification, and then you produce AS prime. Now, the question is, what is the clock cycle time determined by? Over here. That is determined by the critical path delay over here, right? Probably you've done some of this in the past, plus, of course, the delay of the sequential logic. And then I can also ask the next question, which is, what is the critical path, meaning longest delay path in this combinational logic determined by? And that is really determined by the longest instruction to execute. So this sounds bad maybe, right? Meaning longest instruction to execute may take really long because instructions are very different. A matrix multiplication can be an instruction. A memory access can be an instruction, and you may get a cache miss, etc. Right? It could be hundreds of like nanoseconds or so, or more. Okay, so that's a single cycle machine. Each instruction takes a single clock cycle. All state updates are made at the end of an instruction execution. The big disadvantage is the slowest instruction determines cycle time, which means that you get a very long clock cycle time. That's why people have developed multi-cycle machines, which are much more reasonable. This is, I don't think this is realistic at all, but it's good to study it to see bad ideas. Here, instruction processing is broken into multiple cycles, clock cycles or stages. State updates can be made during an instruction execution, but these are microarchitectural state updates. Architectural state update is made at the end of an instruction's execution. When you really are going to finish the instruction, you update the architectural state. The big advantage is now the slowest stage determines your cycle time. So it gives you freedom to optimize. Here, for example, the worst case determines your common case. Basically, everything is worst case, based on worst case. Here, you can optimize for the common case. If you're executing matrix multiplications all the time, optimize for that, right? Make that really fast in your clock cycle, as well as number of cycles to take that. And forget about the square root instruction that you have in your ISA because someone decided that was a good idea to put over there because that's going to take forever and no one is using it. But be careful with that, of course. No one's using it is always a difficult thing to discuss, right? There may be someone in the world using it. Okay, so both single cycle and multi-cycle machines literally follow the von Neumann model at the microarchitecture level. It's good to think about that also. Von Neumann model says sequential instruction execution. So I'm specifically talking about the sequential instruction execution part. Both of these actually don't bring in another instruction into the machine before the previous one is complete. We're going to violate that with pipelining. Pipelining violates that actually, microarchitecturally. So you've probably seen that perspective also. Okay, let me quickly go through this, and then before my multi-cycle, I think I'm going to take a break. So you've seen the instruction processing cycle, probably. Instructions are processed under the direction of a control unit. Instruction cycle is sequence of steps to process an instruction. This is very different from a clock cycle. Clock cycle is related to how long is your clock cycle in the machine determined by your critical path. This is unfortunately called instruction processing cycle also. So fundamentally, there are fetch, decode, evaluate address, fetch operands, execute, store result steps. You've seen this before? Okay, when pipelining, for example. Not all instructions require all 6 steps, actually. And this becomes an issue in pipelining also. So this is what happens, basically. You fetch an instruction, decode it, evaluate address, fetch operands, execute, store the result, update the architectural state, and you fetch the next instruction. Both single cycle and multi-cycle follow this model. So in a single cycle machine, all of those 6 phases that I showed you take a single machine clock cycle. In a multi-cycle machine, all 6 phases of the instruction processing cycle, what I showed you, can take multiple machine clock cycles. In fact, each phase can take multiple clock cycles. So if you go back over here, you can take, I don't know, 10 cycles to fetch, 5 cycles to decode, etc. And you can optimize that. In fact, usually fetch operands from memory takes a very long time. So you really want to not wait for it and make your clock cycle dependent on it, right? Okay. Okay, I think this is actually a better place to take a break because I'm going to switch to data path versus control. So let's take a break. I think let's be back at 15 past. Sorry, a 10-minute break today. And then we're going to cover hopefully what you've seen mostly. But this is in a different way probably, right? Okay. But feel free to ask questions.
I don't know if it's feasible or possible. But right now, the course is only for core courses for the
Do we need to charge this or no? This thing
No, it
would be okay?
yes, maybe
Okay.
3 to 4 hours. So it will be fine.
Okay, that's good. Yeah.
And we also have another one, so we can just change.
Oh, okay, that's good. I don't know. I guess so.
Yes.
I didn't check the online thing. Is that fine?
Yes.
Okay. Okay, that's good.
I basically ask you before I send an email to the study department or anything. Realistically, do you think that process will be done within, say, 3.5 weeks?
We discuss the ICS submission.
Maybe we should. Or this is better.
No,
Okay. All right. Is everything good online? Can you check? Okay, all good. All right. All right. Nope. Well, maybe this is not working anymore. You're still sharing it, right, online? Okay. Okay, it's working now. Okay. So let's take a look at instruction processing another way, which you have covered also probably, data path versus control. Essentially, instructions transform data to data prime, architectural state to architectural state prime. And this transformation is done by functional units that operate on data. These units need to be told what to do to the data, right? And as a result, an instruction processing engine consists of two components. And usually these are distinct components that are designed separately. And then, of course, they interact with each other that are put together. Right? Data path, for example, consists of hardware elements that deal with and transform data signals. For example, functional units that operate on data, multiplication units, addition units, logic units, hardware structures that enable the flow of data into the functional units and registers. And there are many things, wires, muxes, decoders, tri-state buffers, etc. Have you seen all of these before? Maybe tri-state buffer. Okay, don't worry about it. It's not that important. But this is one way of putting signals onto a wire. Basically, you have an input signal, and then you want to put it into a wire, some bus, for example, and a tri-state buffer is put between the input signal and the wire, and then there's an enable signal. If you enable it, this input signal gets connected to the wire. Okay, there are different ways of implementing that. Loading onto a bus, but yeah, we cover this in DDCA. So if you're interested in all of these in DDCA, Digital Design and Computer Architecture has a digital design component that covers some of the, essentially all of these things actually. And we over there we have FPGA exercises, but you guys are don't need to take DDCA, I think. So storage units that store data are also part of the data path, like registers, memory units, etc. And of course, their associated circuitry to address them, etc. There's also a control logic, and control logic consists of hardware elements that determine the control signals. In other words, signals that specify what the data path elements should do to the data. And when you designed or when you've seen a pipeline processor, probably you've seen the different parts, right? There's a control unit and there's a data path. Yes, okay, that's good. I'm going to show you a picture. Don't get scared. This is from a book. Maybe you have not seen the exact picture, but this is an example of a single cycle processor, single cycle MIPS processor. MIPS is an ISA from Harris and Harris. Essentially, the data path is the black parts, and control unit is the blue parts. And control unit takes the instruction as input and generates control signals based on the instruction to control what the data path elements should do to the data that is read based on what's specified by the instruction. Have you seen a picture like this? Okay, great. Maybe not the exact picture, or did you see the exact picture? Not the exact one. Okay.
No, very similar.
Oh, very similar. Yes. I mean, yeah, well, a lot of the material is very similar. But essentially, this is a single cycle processor in the sense that everything is done in one cycle. You essentially have the program counter. You fetch the program counter. You input it into the memory. You read the data from memory, which is the instruction. And then you decode the instruction, access the register file. You operate on the operands and then produce the results. And then if needed, you write data to the memory, or you read data if it's a load instruction from memory, and then write the result back if the instruction specifies it to the register file. And you can see that there are no latches or registers to buffer anything, meaning everything is combinational logic until you latch the data back into memory and the program counter to the program counter. Right? This is the example of single cycle machine, so your clock cycle is very long. And then you can do a fun analysis, which we're going to do a little bit. So, okay, I don't want to harp on too much, but every instruction takes one cycle to execute. Cycle per instruction is strictly one in a single cycle microarchitecture. Now, how long each instruction takes is determined by how long the slowest instruction takes to execute, even though many instructions do not need that long to execute. I already said this, so I will not harp on it again, but let's take a look at this critical path analysis a little bit. So if you want to find out what is the slowest instruction to process, you need to think about how long you actually spend on evaluating these different phases of each instruction. So in this particular analysis, we simplify it a little bit. You have 5 stages. You don't have to have 6 stages, etc. Because you can merge some of these things with each other. Again, I'm going through this relatively quickly because you've probably seen something like this. Now the question is, let's find the critical path. That's a game we play in DDCA, Digital Design and Computer Architecture. Probably you've played a game like this before, critical path analysis. That's good. And to be able to do this, essentially, you need to list all of the instructions in your ISA and list all of the steps to execute an instruction and figure out how long the maximum delay is for each instruction. And this is what's done for a subset of instructions in the MIPS architecture. There are some assumptions, of course. Memory units take 200 picoseconds, ALU and address take 100, register files 50, other logic and wire delay is magically 0, which makes analysis easier, of course, but that's not true in real life, clearly. Now you actually put together different instructions types, and then you figure out that almost always the problem is a load instruction whenever you access the memory. That actually goes through all of the steps, and it takes, in this particular case, 600 picoseconds. Make sense? So this is spreadsheet analysis that you can do quick and dirty. But the real analysis, of course, needs to be done with simulation tools and read the real analysis really in the hardware in the end. But first you simulate. You basically design the processor and then figure out how long each instruction takes. These are the data path and units exercised by ALU instructions in the MIPS architecture on this particular design. And you can see that the critical path is over here and the total is 400. There's also program counter update that happens concurrently, which is much faster, as you can see. And we assume some things. Again, in DDCA, we cover this in more detail. Load actually exercises essentially all of the units across this data path over here. So it takes 600. Updating the program counter is only 100 picoseconds. Store is a little bit shorter than load. And taken branch is actually reasonably short. But you need to find the critical path basically based on the specification of the instruction as well as what is your microarchitecture. Okay. So you've seen something like this before, probably. So I will not harp on it. So this looks not so good, meaning you, assuming all of these are correct, you set your cycle time to be 600 picoseconds, but maybe most of your instructions need 400 picoseconds, right? So you're really optimizing for the worst case. And this worst case is actually much worse than what I showed over here. In modern memory systems, memories are huge. As a result, accessing memory, and it's also off-chip, accessing memory takes hundreds of nanoseconds in some cases. So you don't want the clock cycle time that's hundreds of nanoseconds, right? Okay. So basically, this is a bad design in the end. So let me introduce some architecture or microarchitecture design principles. I think there are many principles that you can come up with, of course, but these are 3 major principles if you want to optimize for performance. When it's critical path design, bread and butter, common case design, and balanced design. Third is balanced design. And single cycle microarchitectures violate all of these. Critical path design means find and decrease the maximum combinational logic delay as much as possible to maximize frequency. We're talking about performance. For energy, you may actually come up with different principles, which we will talk about later on. Basically, you break a path into multiple cycles if it takes too long. And clearly, a single cycle doesn't do any of that. Bread and butter common case design is basically you design, spend time and resources on where it matters most. Meaning, what is the machine going to execute in the common case? Right? This is part the art, of course. Right? If the machine is going to execute 99% matrix vector multiply instructions from the register file, optimizing for something else that may not make sense a lot. And that's the idea of, oh, okay, maybe we could go through accelerators, right? Accelerators actually come from this common case design. What am I going to execute in my workload? And clearly, in this case, we're doing worst case design with single cycle because worst case really determines the common case, common case performance. Balanced design is essentially you balance instruction and data flow through hardware components, eliminate bottlenecks as much as possible, balance the hardware for the work essentially. And this is also violated, but I will not go into that in detail. We'll see balanced design later on. So these are the design principles. It's good to think about these when you're designing a high performance system. How am I actually satisfying them? How am I violating them? Can I do better, essentially? Sometimes balanced design is very hard to satisfy. For example, today's machines are actually not so bad at these two, but they're terrible at the balanced design. And what I'm referring to over here is the balance between compute unit and memory. Essentially, compute unit has a lot of performance, but accessing memory is done using a thin pipe, meaning a low bandwidth memory bus. As a result, there's a huge imbalance between compute and memory today. And that's what we'll foreshadow into thinking about like future like processing in memory type of architectures. Why don't we put compute units inside the memory itself so that we don't go through a thin pipe in the microarchitecture? Okay, so essentially, single cycle microarchitecture doesn't do too well. We're going to compare multi-cycle to these principles also. Yes, please.
What is the difference between putting more memory into the CPU compared to putting compute into the memory?
That's a great question. We can talk about when we come to it. But essentially, you can put more memory into the CPU where the logic is. The question is, how much memory can you put over there? What we're limited by today is the technology. The denser memories require a fabrication process that's very different from how we fabricate CPUs, meaning logic today. If you want to have very dense, huge memories, you need to design logic for those huge memories, let's say. Okay. So basically, there's a fabrication process dichotomy, unfortunately. People have not figured out how to make dense memories using the fabrication process CPUs are fabricated with. But that's a great question. If you figure that out somehow, then maybe you get rid of the bottleneck. A lot of people tried. That doesn't mean that you should not try, though. Okay. So always we're going to ask this question in this lecture. And I think it's always good to ask this question to do better going into the future. The question is, can we do better? And I think I've already given you the idea of how to do better, multi-cycle microarchitectures. But let's examine it in a little bit more detail. And then we're going to go into pipelining. So the goal, as we discussed in multi-cycle microarchitectures, is to let each instruction to take close to only as much time as it really needs. I say close to because you cannot be perfect over here because we're going to add some overhead also, which is latching overhead, sequencing overhead, etc. So the idea is to determine clock cycle time independently of instruction processing time. Each instruction takes as many clock cycles as it needs to take. And there are multiple state transitions per instruction. And the states followed by each instruction is different. Okay, let me go back over here because this idea is the first part of the idea, even though it may not sound like an idea, it's really part of the core idea. Basically, I don't say these are the instructions that I'm going to execute and this is my clock cycle. I say I'm going to have a high clock cycle and I'm going to design my machine so that I can achieve that clock cycle time. Now, you can argue that that high clock cycle is good or bad. You determine different ways, but you actually have freedom to decide your own clock cycle, say 100 gigahertz. And you can design a machine to do that with multi-cycle. You cannot do that with single cycle. Okay. So basically, it looks pictorially like this. You start with an architectural state. You transform it to a microarchitectural state, process part of the instruction in one clock cycle, store the results, intermediate results somewhere, which is going to be our overhead, process part of the instruction in the next clock cycle, and then process the next part, next part, next part. And these number of steps may depend, actually, they do depend on how, the type of instruction that you process. And eventually, you generate the architectural state prime at the end of the clock cycle. Make sense? Well, at the end of a clock cycle, at the end of the last clock cycle to execute the instruction. There's not a single clock cycle, as you can see over here. An add may take 4 clock cycles. Multiply can take 10 clock cycles. And memory access can take as long as it needs to take, because it may go to far away, right? Today, we actually have far memories also, not just local memories, but remote memories. Okay, especially in data centers. So this is actually one of the designs that is proposed by Maurice Wilks, who is essentially a leading computer architect, one of the fathers of computer architecture, let's say. Essentially, the realization is that you can implement the process instruction step as a finite state machine. Actually, everything is a finite state machine, but now you actually implement the process instruction step as a finite state machine that sequences between states and eventually returns back to the fetch instruction state. And I'm going to show you an example of this finite state machine. A state is really defined by the control signals asserted in it. In a given state, you say, okay, these are the control signals that I assert. These are the control signals that I deassert. And that is actually determining what the data path does. And that's the signature of the state. In fetch state, for example, I read from the program counter and latch it into the instruction register. And that's fetch state. Well, not read from the program counter, input it to the instruction memory, which could be a single memory at this point, and then latch it into the instruction register. And the control signal that enable you to do that are asserted in that state. That's my fetch state. You can have fetch 1, fetch 2, fetch 3, fetch 4, fetch 5, 5 fetch states. Control signals for the next state are determined in the current state. So you overlap the computation and the data path computation in the current state with the control signal generation for the next state. This is a good design principle so that your control signal generation doesn't become the critical path. Earlier in the picture, we looked at actually data path, but control signals may become the critical path if you have a bad design. In general, control signals should not be your critical path. Okay, I'm giving you a lot of thoughts over here and ideas, but hopefully you've seen some of this before. So this is an example of a multi-cycle microarchitecture finite state machine, a subset, again, from Harris and Harris. For example, this state is the fetch state, and it basically specifies which control signals are asserted, which ones are not asserted, etc. And then you decode the instruction, and decode state has some signals. And then based on what you decoded, based on the opcode, you jump into different sequence of states. Right? For example, if it's a load word, you have a memory address generation state over here. And then based on whether it's a load word or store word, the next state is either memory read or memory write. And then once the memory write is done in a store word, you go back to fetch the next instruction with the next PC, which should have been incremented in one of these states over here. Okay, for load word, you do write into the register. So now you can actually optimize your finite state machine such that hopefully you achieve your clock cycle time. Right? None of these things that are described here should not exceed, well, at least the combination logic delay to implement them should not exceed your clock cycle time. Makes sense, right? Okay. So again, I'll go through this relatively quickly, but instruction processing cycle is divided into state. A stage in the instruction processing cycle can take multiple states, multiple clock cycles. A multi-cycle microarchitecture sequence from state to state to process an instruction. And the behavior of the machine in a state is completely determined by control signals in that state. I'm harping on this because this is really important. Which means that if multiple different instructions actually share the same behavior, they can use the same state, and then you can branch out. So you can actually optimize your finite state machine also. And the behavior of the entire processor is specified fully by a finite state machine. Okay, in a state, as we discussed, control signals control two things: how the data path should process the data, and how to generate the control signals for the next clock cycle. So this was our single cycle microarchitecture. We're going to keep most of it the same to do a multi-cycle microarchitecture, but we're going to optimize. So this is a multi-cycle microarchitecture, which probably you've seen also, correct? Again, maybe not the exact same thing, but what we've added over here is we still have the control unit over here. So let's go back. Control unit is a little bit more complicated because we have intermediate states, meaning these registers over here that we added so that we can latch intermediate data. Before, we didn't have any latches in between. Now we have latches so that we can optimize the clock cycle. So the clock cycle is determined by this stage or this stage or this stage. Basically, you need to follow how the data flows through the registers. Okay, so we've added a lot of registers, as you can see, and we've added some more control signals, etc. Okay, let me these are extra registers that are not needed in a single cycle design. Make sense? So we have hardware overhead. We paid some cost. But we also actually gained something. If you paid attention to the previous slide, which I don't expect you to because this is so small and far away, I can barely see it from here. Yeah, basically we saved some things. We don't have that many ALUs as before. We can actually get away with a single ALU. We're frugal. Why? Because in the previous design, in the single cycle design, we needed to have as many ALUs as needed to execute an instruction in a single clock cycle. You cannot reuse the same ALU across different stages of the instruction. You have to have, for example, if you're doing an add, you need to have an adder. And then you need to update the program counter. That requires an adder also, right? You cannot reuse them because you're doing everything in a single clock cycle. You need to have combinational logic to do everything that is possible in an instruction concurrently. But if you actually say, okay, I'm going to do part of an instruction in a clock cycle, you can get away with a single ALU, which is nice. You can actually be also consolidated instruction and data memory together also. Instead of having separate memories, instruction and data, we have the same memory over here. Again, in a similar way. You can, when you're fetching an instruction, you use the instruction part. When you're loading data or storing data, you use the data ports. Okay. Okay, so basically this is a summary. In a single cycle microarchitecture, we have low clock frequency and high hardware cost. I've added that now. In a multi-cycle microarchitecture, we have higher clock frequency. Simple instructions take only a few clock cycles, and we can reuse expensive hardware across multiple cycles. That's also nice. Now, the downside is we have hardware overhead for storing intermediate results, as I've shown you, and we have sequential logic overhead paid many times for each instruction because you have to latch the data at the end of the clock cycle, and that eats from your clock cycle. If you think about digital design, there's useful work that you do in a clock cycle, which is processing the data, and there's the overhead, which is sequencing, right? You need to latch the data. And as you make your clock cycle smaller and smaller and smaller, the useful work becomes a smaller fraction because the sequencing overhead starts to dominate. So it becomes, at some point, if you actually make your clock cycle extreme, maybe even less than 1 gate, your sequencing overhead may be higher. So in the end, as you pipeline deeper, well, I shouldn't use the word pipeline, as you make your clock, because we're not pipelining necessarily, that's a higher level concept. But it applies to pipelining also, which I'm going to say. As you make your clock cycle smaller and smaller, at some point, it doesn't make sense to make your clock cycle smaller because you're paying a lot of overhead, and your latency of processing an instruction actually increases because your instruction goes through many clock cycles where most of the clock cycles spent sequencing, right? Doing useless work, essentially. Well, it's not useless work, but doing sequencing overhead so that you can store the data in latches. Okay, so multi-cycle requires the same design as steps as single cycle. You still do a data path and control logic, but you add these latches as we've seen. So one advantage of multi-cycle that we didn't discuss is flexibility. And this is actually a huge advantage. Let's say what we assumed actually something really bad over here, which is memory takes 1 clock cycle, right? But in modern systems, memory takes maybe hundreds of clock cycles, right? So how do you fix that? What if memory takes 500 cycles? Or what if memory takes an unknown amount of cycles? Basically, you have another signal. You add another loop over here, says if the memory is ready, if the memory is not ready, you stay in this cycle. If the memory is ready, then you move to the next cycle, next stage, next state in the machine. Does that make sense? So there's a lot of flexibility, and you can also add other instructions or write a program that actually goes through this finite state machine as a hardware designer. Microcode is an example of this, but we're not going to cover that. Any thoughts? Any questions? These are all familiar concepts. Yes.
Earlier, I didn't quite get how we could reuse the same ALU when we have like multi-cycles.
Mm-hmm. So, for example, you have a fetch state over here. It's fetching. It's using the ALU. There's only one ALU in this. Yeah. And then you have, let's see, where is this? Execute stage. Mm-hmm. It's using the same ALU, yeah. Right? The reason you can use it is because you latch the data from the fetch. Mm-hmm. In a single cycle, if you do that, which data are you going to supply to the ALU? Does that make sense? You're incrementing PC to PC plus 4, mm-hmm. or you're doing some operation. Your instruction requires both, yeah. Add instruction. Mm-hmm. So you really need 2 ALUs so that you can increment PC plus 4 while concurrently, maybe not concurrently, because data has flown through the first ALU. You fetch the instruction, you decode it, etc. But you didn't really latch the result, right? If you go back and input the same input the registers. Or input the register IDs or registers that you read into the same ALU. Mm-hmm. Now you need to change the control signals. Yeah. You could do that, but that would change your PC. Yeah. Now you wouldn't be executing the same instruction. Okay. Does that make sense? Yeah. The reason is there's no latching in the first in the single cycle machine.
Okay. Thank you.
Sure, you're welcome. Any other questions? Okay. So let's look at the benefits of multi-cycle design. So this is actually good for critical path design. Again, using our framework, principled framework. You can keep reducing the critical path independently of the worst case processing time of any instruction. This is great. It gives you flexibility. You can optimize for the common case. You can optimize the number of states it takes to execute important instructions that make up much of the execution time, for example. You focus on that part of the finite state machine as opposed to some not so commonly executed part. And you're more balanced. There's no need to provide more capability or resources than really needed. And this is what the previous discussion kind of points to, right? As opposed to having 3 ALUs, you may you may get away with one, depending on your instruction set, of course. Okay, I think I have discussed this. An instruction that needs resource X multiple times does not require multiple X's to be implemented. That's kind of a summary. Okay, I think I said that. But there are downsides we've seen also. You need to store the intermediate results. There's hardware overhead, register setup and hold overhead, what I call sequencing overhead. And we're going to talk about this downside to build up to pipelining, limited concurrency. Only a small part of the machine is used at any point in time, right? So for example, when you're fetching, only the fetch part is used. But there's a lot of stuff that's part of your machine, right? ALU, memory, register file access, none of that is used because you're actually executing only a part of the instruction. And this becomes worse and worse as you reduce the clock cycle time, as you make your machine higher frequency. Now you can say this is okay. The hardware is useful, but then you're not utilizing your hardware in the best way possible. Okay, before I go into it, have you seen the performance analysis equation? Does this look familiar? Basically, execution time of an entire program is number of instructions times average cycles per instruction times clock cycle time. Yes? No? Maybe you don't remember. Maybe not. If you don't remember it, probably not. This is also called, some people call it the iron law of computer architecture, but it applies to some general purpose systems. Actually, it's a good way of thinking about execution time. So execution time of a single instruction is really CPI, cycles you take to execute the instruction, times the clock cycle time. This makes sense. Execution time of an entire program is this summed over all of the instructions you execute in the program. You can also think about that as number of instructions times average cycles per instruction in your program times the clock cycle time. Now, this gives you a way of thinking about how to optimize your system, right? If your goal is to maximize performance, you have three things to play with, right? Now, number of instructions, you can play with it at the compiler level or the programmer level. You can write a different algorithm, different program, etc. We're going to assume that the number of instructions is the same. If you want to actually fairly compare microarchitectures, you should either assume that or figure out the best number of instructions that provides the best overall performance for each architecture, which is not an easy thing to do. So fair comparisons are actually very hard in architectures in general. But anyway, assume that number of instructions is the same. We can play with average CPI and clock cycle time at the microarchitecture level. Right? Microarchitecture usually cannot play with the number of instructions because that's specified by the program. So a single cycle microarchitecture performance says CPI is 1, clock cycle time is long. Whereas multi-cycle, CPI is different for each instruction. Average CPI is hopefully small, and clock cycle time is short. So you gain on both parts, essentially. Yes. Well, no, sorry, you don't gain on both parts. Let me correct myself. Your average CPI is higher than 1, but clock cycle time is much better, hopefully.
Is the average CPI calculated for each program individually?
Yes, exactly. Mm-hmm. And when you evaluate a machine microarchitecture in terms of CPI, you can actually aggregate across many programs also. This is my average CPI on this set of programs. This is my average CPI on this set of programs. And overall, this is my average CPI. Okay. But clock cycle time doesn't change across programs. Yes?
So just a bit branching out.
Yeah.
How would you, what's a good metric for comparing, let's say, memory loads? Because this will obviously be
well, like if your workload is memory intensive, your average CPI may go up significantly, right? So you can still compare. This is still applies. Yeah, across different microarchitectures. Well, across different architectures is different. Across different microarchitectures, you can do some comparisons, right? You run the same program, for example, across different microarchitectures, and you can try to optimize CPI and clock cycle time. Anyway, we may get into the memory. We'll get into memory more. What this doesn't take into account is clearly energy, for example, or data movement overheads in terms of energy. But a lot of things get reflected on the average CPI in the end. So if you have a very memory-intensive workload that waits for memory, average CPI is very high. Okay, so basically, I think my point here is in multi-cycle, we have 2 degrees of freedom to optimize independently. Whereas in single cycle, we have 1 degree of freedom, which is clock cycle time, but we don't have a lot of freedom in that degree of freedom either. It's determined by the worst case. Okay, the question is always, can we do better? And now we're going to get into pipeline. Essentially, the question is always asked, what limitations do you see with the previous design? Right? In this case, I already given you limited concurrency. Some hardware resources are idle during different phases of the instruction processing cycle. In fact, most of the machine is idle. Can we use it for something else? Fetch logic is idle when instruction is being decoded or executed, or making a memory access or writing the result back. Most of the data path is idle when a memory access is happening. Right? So can we use idle hardware to improve concurrency? And the answer is yes. Well, why do we want to do that, first of all? More concurrency is higher instruction throughput, meaning more work is completed in one cycle. And the idea here is when an instruction is using some, meaning we can reduce the cycles per instruction. Right? Another way of thinking of it, we can improve instructions per cycle. But we'll get into that. These are two sides of the same coin. So basically, the idea is when an instruction is using some resources in its processing phase, process other instructions on idle resources that are not needed by an instruction. For example, when an instruction is being decoded, fetch the next instruction. Right? When an instruction is being executed, decode the next instruction. When an instruction is accessing data memory, execute the next instruction. When an instruction is writing its result into the register file, access data memory for the next instruction. So this is based on sequential execution. It doesn't have to be the next instruction. It could be any random instruction, but that will make your life very complicated when you're updating the architectural state. So next instruction is a good idea. Okay. So basically, you can have different instructions in different stages. So assume that we have these 5 stages. What we can do is one instruction is writing its result, another instruction is executing the ALU, another instruction is accessing the register file and being decoded, another instruction is being fetched. Right? And now you need to change the control logic to make sure that right control signals are generated for instructions in different stages. Right? So clearly, we need to be more careful than this. We cannot just declare victory. We need to actually redesign the entire thing to make sure it works. And we're going to look at that in a little bit. So I've given you the basic idea. Systematically, we pipeline the execution of multiple instructions. This is similar to assembly line processing in factories. Basically, instructions go through an assembly line. Every instruction goes through every stage in the pipeline. I think we've already said this. Divide the instruction processing cycle into distinct stages of processing. And ensure there are enough hardware resources to process one instruction each stage and process a different instruction in each stage. Instructions consecutive in program order are processed in consecutive stages because of the sequential execution model that we assume. And the benefit is this is increasing instruction processing throughput, 1 over CPI, or viewed another way, it reduces cycles per instruction. It doesn't reduce the cycle per instruction of an individual instruction. An individual instruction actually still goes through the same cycles, except you're doing more instructions, so average CPI reduces, right? So it doesn't help the latency of an individual instruction. In fact, it's going to hurt the latency if you pipeline more because of the hardware overhead, hardware register overhead, sequencing overhead, but it improves throughput of the overall instruction stream. Make sense? Okay, so hopefully you know the idea. So downsides, it's good to start thinking about this because there could be many downsides also, and we're going to cover. The beauty is, how do you handle the downsides? Can you have a better model, etc.? So that's going to build up. We're going to build up the out of order execution with this. But before we get ahead of ourselves, let's take a look at pipelining a little bit more. So this was multi-cycle. You have assumed that you are doing 4 cycles per instruction. These are your stages. And if you pipeline them nicely, you can actually finish 4 cycles, 4 instructions in 4 cycles, as you can see, right? Because things are nicely pipelined over here. And at the steady state, this is called the steady state, where your machine is full of instructions, that's where you can see that you're executing 4 instructions concurrently, right? Except in different parts of the machine. So this is nice. Now you have, on average, 1 instruction completed every 1 cycle. Here, 1 instruction is completed every 4 cycles. So you improved CPI by 4x. So your performance may improve by 4x, except maybe pipelining overhead will be worse over here for the reason. So clock cycle time may be lower over here. But if you can keep your clock cycle time the same, your performance may improve by 4x. That sounds great. The problem is life is not always this beautiful. First of all, you may not be able to have a nice clock cycle time kept the same. We're going to see that a little bit. And you may not be able to fetch the next instruction because that requires you to know what's the next instruction address. If you're doing sequentially, that's good. But what if a branch happens? What if this instruction is a branch and you need to decide what is the next instruction? If it's a taken branch, if it's a not taken branch, again, you're fetching sequentially, that's good. But what if it's a taken branch? You don't know that before you execute the instruction, so you'll have pipeline bubbles, etc. And what if instructions are dependent on each other? Right? Maybe you actually need to stall the pipeline. Okay, so this is an aside. This is one of the first pipeline computers, IBM Stretch. You can carry it in your pocket, as you can see. And the price is what everybody in this room can afford, I think. I cannot afford that. Okay, it's fun. So that shows that how technology scaling has been successful, right? Okay, so an ideal pipeline, we would like to increase throughput with little increase in cost, hardware cost in case of instruction processing. So pipelining can be applied to many concepts, actually. We talked about assembly line, right? Actually, that's how a lot of pipelines were. People started thinking about analyzing pipelines in operations research, for example. There's a field that's dedicated to analyzing large-scale production systems. And pipelining is a big component of operations research, at least the old type of operations research. So if your pipeline should be efficient, if you want your pipeline to be efficient, ideally, you should repeat identical operations. The same operations repeat on a large number of different inputs. For example, when you're doing laundry, if you actually have a laundry, let's say, business, you get a lot of loads, and they all go through the same stage. You do the identical operations on them, right? You put them into a washer, and then you put them into a dryer, and then you fold them, and then you give it back to the customer. There's no difference, hopefully. There may be, I don't know. I'm not in that business. From my perspective, it's similar. But that's where the analogy ends. Don't push it further. Okay, and then you want to repeat repeat independent operations. So different loads are independent of each other in the laundry, right? So there's no dependencies between repeated operations, and this makes your life easier because you could keep pushing things without thinking about, oh, this load actually should stop because my shirt needs to be processed first. But there are dependencies also over there, as you can see. Okay, and then if you want to actually have a good clock cycle that's partitioned nicely across the stages, you need to have uniformly partitionable sub-operations, basically processing such that processing can be evenly divided into uniform latency clock cycles in this particular case. That's true for laundry also, because, for example, when you're doing laundry, usually the dryer takes the longest, and that becomes a bottleneck, right? If your clock cycle is determined by the dryer, then your throughput will be limited. So if you're running a laundry business, probably you pay more for the dryers and get more dryers for a given number of washers, right? This is why dryers are expensive from my perspective, because there's more demand on the dryers because they're slower. Okay, anyway, so automobile assembly line doing laundry are actually reasonably fitting examples. The question is, what about instruction processing cycle? Do we get all of these properties nice? And unfortunately not. And that makes things interesting and nice. So let's take a look at this ideal pipelining. So what we want to do, this is like a single cycle machine, right? You have some combinational logic to execute instructions, t picoseconds. Ideally, when you pipeline it, you would like your throughput to be doubled, right? If you have a two-stage pipeline. Unfortunately, you have a sequencing overhead, so that's not going to be possible. If you pipeline it for three things, you need to basically decide how to pipeline it also. That's also essentially a design optimization problem. Ideally, you would like throughput to increase linearly with number of pipeline stages. But unfortunately, more realistic pipeline, you have a sequential logic delay, and you pay that sequential logic delay multiple times, just like in a multi-cycle processor in a realistic pipeline. So throughput to k stage looks more like this over here, t over k plus some sequencing delay. So this register delay reduces throughput. This picture still assumes that you can evenly divide the work nicely. That may not be also possible, right? Because your boundaries of memory, your boundaries of registers, your boundaries of ALUs may not really nicely divisible as t over k. So it's good to think about that. So a lot of digital design actually works on this sort of thing, how to optimize a pipeline, for example. There's also cost. I'm not going to talk about energy, but cost energy is more complex. If you look at non-pipelines, you have some number of gates. This is a single cycle again, and then some registry cost. If you have a pipeline, if you're lucky, if you nicely divide the gates across stages, your gate cost doesn't increase. That's not real. Usually your gate cost increases. You multiply the register overhead by the number of stages. registers increase hardware cost essentially. Again, this picture ignores resource and register replication that's likely needed, G over K and R over RK. Okay, I'm going through this relatively quickly because probably you've seen things like this, right? Have you designed things at that level, lower level, or? Okay, some of you maybe. Okay, now let's take a look at, I think we've already seen all of these processing cycles. So this was our single cycle microarchitecture. This is another example of single cycle microarchitecture. Again, that looks like this, what I've shown you. When you're designing a pipeline, you need to divide the single cycle microarchitecture into some stages. And let's assume that this is the division that you came up with. You need to have some more things added, and you need to be careful about things that look like this, right? You actually are processing an instruction over here, and this instruction is determining, this is a branch, for example, or the target of the branch. This instruction may change the program counter over here. So you need to be careful about these backward loops that come so that you actually do the right thing for the right instruction, because different instructions are in earlier parts. So assume that this is a partitioning that someone has done. There's always the question, is this the correct partition? Assume that you want to design a 5-stage pipeline. Your throughput should improve by 5x normally, right? But if someone came up with this partition, you can say, why didn't I have 4 stages or 6 stages? Why not different boundaries? It's always good to think about. Let's take a look at the throughput of one of the pipelines. This is here. This is a multi-cycle or a single. I guess it's a multi-cycle design, but it doesn't matter. One instruction is finished every 800 picoseconds over here. No, this is a single cycle design. Assume that everything takes 800 picoseconds. Well, in this case, it doesn't matter because they're all same instructions where the assumption is the same. Here, each instruction, you get one instruction finishing every 200 picoseconds with the partitioning that we have seen. And the reason, and the throughput improvement you get is 4x as opposed to 5x, even though you have 5-stage pipeline, right? Why? Yes.
Our cycle is like 200 picoseconds. Like it isn't like
exactly.
800 divided by 5.
Exactly. Yes. It's not 160. It's 200 because we couldn't somehow manage to divide it. Exactly. Basically, this is we couldn't uniformly subpartition the operations, right? Essentially, that's the last part that I discussed in an ideal pipeline. Okay, basically half of the clock cycle is wasted in 2 stages. Another way of looking at it. There's some internal fragmentation that happens in the clock cycle, and usually things could be worse than this. Okay, so you need pipeline registers, as I said. If you want to pipeline things to K stages, you need to add some pipeline registers so that you can store the intermediate results, and that adds to the overhead as well. So for example, you need to store PC+4 and you need to propagate it until you actually may need to use it, because your instruction you're processing over here may be a branch, and you may need it for some reason, etc. Next PC, actually, you may need it over here. You need to propagate some parts of the instruction register, data elements that you fetch, immediates, etc. So these registers actually grow after you decode the instruction, and then they start shrinking because you use some of the data in the stages that are later. So they're not actually equal. This picture kind of shows that they're kind of equal, but they're not actually equal in terms of size. Okay, you need to make sure no resource is used by more than one stage. So all instruction classes must follow the same path and timing through the pipeline stage. This actually leads to some other overheads. So this load word is being decoded, executed, memory. Load word is nice because it actually utilizes all of the pipeline stages that we have over here. But if you do an add, for example, it doesn't do anything in this memory stage. So not all instructions use all stages in the pipeline. And that leads to something that we don't normally think about, but actually it has a performance impact. If you could actually do something else, then you wouldn't waste that, or you could do something more useful. It's much harder to do, of course, in a linear pipeline like this. Okay, this is the example of a pipeline control. Essentially, you have the same control unit as a single cycle processor, except you delay the use of the signals until the appropriate point in the pipeline. So you generate the control signals, you latch them, and then you move them through the registers. Some control signals are needed over here. So you have only 2, for example, in this particular case. And some other control signals are needed over here. But you need to store the control signals that are needed in this stage, as well as every other stage after that. Right? So your pipeline registers actually are quite large. Okay, let me finish this and then we'll be done. Essentially, this was our ideal pipeline. we want identical operations, independent operations, and uniformly sub-partitionable operations. Unfortunately, we don't have an ideal pipeline and instruction processing unit. We have different instructions, not all need the same stages. Forcing different instructions to go through the same pipeline stage leads to external fragmentation. Uniform sub-operations, you have different pipeline stages that are not the same latency. You need to force each stage to be controlled by the same clock, meaning you're wasting part of the clock. Some pipe stages are fast, but still have to take the same clock cycle time. That's internal fragmentation. And finally, we're going to start with this next time, independent operations. Instructions are not independent of each other. So you need to actually control the pipeline so that you detect and resolve inter-instruction dependencies so that you don't get the wrong results. Right. Okay, this leads to pipeline stalls. Okay, so that brings me to issues in pipeline design that we're going to cover next week. And then from there, we'll build a pipeline processor and then an out-of-order execution processor. Does that sound good? All right, cool. We'll see you next week.
Quick question.
Sure.
I think it was slide 88 or something like this.
Okay.
Where you mentioned with multi-cycles that you gain flexibility.
Yes.
Like memory is really large.
Yes, yes.
Takes a long time.
That's a finite state machine, yes.
What did you mean by this flexibility?
So basically, you can easily add a control signal from memory and change your finite state machine easily so that you make a very local modification.
But
Does that make
single cycle you can't do that?
Single cycle, if your memory takes longer, your clock cycle needs to increase. Whereas here, your clock cycle doesn't need to change.
But I mean, this isolated stage will anyway be longer because the clock cycle is
Not necessarily. In this particular case, the clock cycle, you can keep exactly the same, except the memory says, okay, I'm done at this point. So you can stay in the stage as long as memory is not ready without changing your clock cycle.
But the thing is, if I don't go to the next stage, I have to wait.
Yes.
This wait increases my clock cycle.
No. It doesn't increase your clock cycle. It takes your program. It increases your how many cycles you take to execute. Basically, you're in this stage for more cycles now, but your clock cycle, yeah, exactly. Just repeat waiting in that stage essentially.
Yeah,
Yes.
that makes sense.
Yes.
And you mentioned that if you do pipelining, not pipeline, staging, you can basically reuse resources like ALUs. But if you do pipelining,
yes, no. Basically, we go back. Yeah, that's a very good point. We're going to get to that. That increase your hardware cost. So that's a nice thing in a multi-cycle design. But if you want to increase your throughput, unfortunately, you have to add back all of them. Yeah.
Professor, can I ask if it is